Good evening. So before we continue, I just wanted to go over a few announcements. Your next big deliverable or due item is Project 1, which is going to be due on October 30th. You may notice here that I have reduced the weightage to 15% so that the weightage for the three exams can be kept consistent as 20, 20, 20. So that's 60%, 15% for project 1, 5% for the DFT coding exercise, and then 20% for project 2. So that the optional comprehensive final will still remain 60%. And if you go under project 1 description, I highlight a couple of things that I want you to do. You need to not just leave it with a general solution. That is, you can select any problem from this range, do the Bessel series solution. It will be a function, sum of the first kind and Bessel function of the second kind. But you shouldn't just leave it in terms of arbitrary constant. You should select suitable boundary conditions to get a particular solution. So you can be creative about it, and you can apply some physics knowledge to come up with a set of realistic boundary conditions. And you can also try to do a scale analysis of your solution. I'll just leave it there. Like if you get a solution, if it contains different values of n, you can try plotting different functions or different basis functions, or what value n should take so that the solution will turn out to be what does it correspond to for n equals 1, n equals 2, and so on, because all of them are valid solutions. So you need to do a little bit of analysis, light analysis, after you get the solution, so that I know you know how to work with the obtained solution. Okay. And the overall goal of this programming exercise is to prepare you for project 2. If you just skip this and think I'll take a hit and let go of this 15%, you will also probably lose your project 2 score, because this skill is needed there. Okay, so please work on this. Submission is October 30th, as I mentioned before. Remaining things are all the same. So I've reposted this for you to look at. And we are here back in October 16th, where we'll continue discussing ODE. Today I want to discuss Laplace equation. Let's see how far we can get. So last lecture, we started seeing two types of equation. One is the wave equation, which is describing wave propagation in a domain. We did consider only one-dimensional domain to keep it simple, and also what is called the heat or diffusion equation. So we had partial u over partial t equals c squared, second derivative of x. Both these problems involve both time and space, so your solution is a function of both x and t. And we are talking about a domain which is one-dimensional, x equal to 0 to x equal to L. And you need to know boundary conditions at both ends. Boundary conditions need to be specified at both x equal to 0 and x equal to L, because those are the boundary points, everything else is the interior. So this function here is defined in the open interval x less than L, 0 less than x less than L. And we also need to know the initial condition, which is the function of, which is the value of u at time 0. We'll call this f of x. In the case of heat equation, you just need to know the initial value of the function. For the wave equation, you also need to know the first derivative with respect to time. We call that g of x. That is, for wave equation, you need both. For heat equation, you just need the initial condition for U. And we saw the solution for U in terms of a Fourier series. And the starting procedure is always same. Separation of variables. To assume U is a product of two functions f of x times g of t. So this was the overall summary of last lecture. Of course, we did see the individual solutions for wave equation and heat equation. If you want to remember, because you have a second derivative in time, you could remember that as solution is composed of trigonometric functions of both f and g. I'm sorry, I should state it as solution is f and g both assuming trigonometric forms. For diffusion equation, we have the solution is a decaying exponent in time multiplied by a trigonometric function in space. Just a review of last time, okay? So what we saw for the wave equation, the types of boundary conditions we saw, we had at both ends u at x equal to 0, comma t is 0, and u at x equal to L, comma t is also 0. So fixed at both ends. Fixed at both ends. That is the boundary condition. For initial condition, you have u of x comma t equal to 0 equal to f of x. This is initial displacement. And u t, that is the derivative with respect to time at initial time, that is g of x, meaning the initial velocity. This is what we saw last time. Okay. For the heat equation, we could have, for example, we'll call this u naught and ul. If u is specified, that is called a Dirichlet boundary condition. If partial u over partial x is specified, that will be called a Neumann boundary condition. You could also have something like this. Alpha u plus beta partial u over partial x equal to gamma. This is called a mixed boundary condition. Still linear, but alpha, beta, gamma are constants. Okay. For wave propagation physics, that is the way it works out. Usually, we treat the ends to be fixed. So this function, this type of boundary condition is very common for wave equation. But for heat equation, especially if you think of a conduction heat transfer situation, you could specify either constant temperature or you could have a constant flux boundary condition. So here is, I didn't go over the heat equation derivation in general, but I want to make one remark regarding boundary conditions. Because if this is zero, in one of the steps, you would get something like sine PL equal to 0, which gives you the solution P equal to n pi over L. This was one of the important steps. But in this case, if your function is given some value, arbitrary value, which is non-zero, if you end up with sine PL equal to U naught, that's like saying here is sine PL and here is U naught. How will you solve practically for these values of x at which the function attains U naught? That's practically, you can see that's a problem. Do you see that issue? Like if I just give some arbitrary value which is neither 0 nor 1, it is not impossible, but it's very, very, very messy. So how do you reduce any given problem to something that is mathematically easier? That is the question I'm trying to address here before we move on to the next type of different differential equation. Okay. Any thoughts? That is, suppose you have a problem, that is, you have a heat transfer problem, and to emphasize that it is heat transfer, I'll write partial T over partial T is K times second derivative with respect to temperature. And you have, let's say, T naught and TL. And this is typically a value, let's say 273 Kelvin, 300 Kelvin, some Kelvin. How do you make this problem easier to tackle and make it less gross? This has nothing to do with separation of variables. All I'm asking you to think about is a little bit of scaling logic. Somebody was going to say something? Normalize is correct, but how would you normalize? I have T naught and TL. And I'll say initial temperature T of x comma T equal to 0 will have it some f of x. Especially in heat transfer temperature modeling, this tip that I'm giving you will apply. Temperature is relative, right? So if you subtract TL from both the ends, that is, replace T with T minus TL or T minus T naught if you want. We call this tau. Okay. So in that case, I could write the new variable would be partial tau or partial time equals k squared partial tau over second derivative of tau with respect to x. And this will be T naught minus TL, and this end will be 0. I'm sorry, the other bit. This is 0, tau equal to 0, and tau equal to TL minus T naught. 350 Kelvin minus 300 Kelvin, something like that. If TL is 350, T naught is 300 Kelvin, you get 50 Kelvin. Okay. And then you introduce another normalization. I mean, I'm doing it in 2 steps, but you could very well do this in 1 step, which is you can call, say, gamma is tau divided by TL minus T naught. So you could replace this equation with partial gamma or partial T, maybe a different value with different symbol. What symbol shall we use? Call it delta. So delta over T equals K partial delta squared over partial x squared. So now your boundary conditions will be gamma equal to 0 and gamma equal to 1. Much simpler than dealing with some obtuse numbers. Okay. And if you prefer, you could also normalize the x value. Instead of it making it run from 0 to L, you can make it run from 0 to 1 by introducing a scaling factor. That's up to you. Like you can normalize the space and time to make the equation more compact, as you would have seen this in many papers. They non-dimensionalize the equation before they are solving it. So now your boundary conditions don't look that bad. You have 0 and 1. So if you write out the solution, writing out sine PL equal to 0 will give you easily deducible values for P. And similarly, if sine PL equal to 1, this is also not bad. You can figure out what values of P will get you 1. So when you get a problem to solve, instead of rushing into solving it with all the techniques you know, spend a few minutes thinking about how to scale it so that your solution can be simplified. Okay. All right. So then I want to start with the next type of differential equation. So the third in our list is Laplace equation. And we'll stick with the Cartesian coordinate system for now. So partial derivative of x, second derivative, plus with respect to y equal to 0. Our domain is obviously extending in 2 dimensions. And for simplicity, we'll consider a square domain. This is L comma 0, 0 comma 0, 0 comma L, and L comma L. And to also simplify the boundary conditions further, we'll assume U is 0 on 3 faces except the top. Now, this equation appears in many fields, in steady state wave propagation, in steady state heat transfer or diffusion, most kinds of fluid mechanical equations. This is the dissipation term or the viscous term. So this, your context could vary. Electrostatics, especially electrostatic, elasticity appears in many places. Depending on the context, your quantity could represent a temperature or a displacement or anything else. Okay. I generally use temperature because it comes easy to. Your context could vary. Okay. So this type of boundary condition in which we specify the function value on all sides is like holding the temperature constant on all sides, except on one side we hold it as a constant that varies with space. You could also have a boundary condition in which you can specify to be a constant. That is, the flux on this phase can be said to be a constant that depends on your experiment. Or if it happens to be in this phase, wait, this is x equal to 0. So this here, the flux across this phase be partial u over partial x at x equal to 0 equal to k, and this is partial u over partial y at y equal to 0. Let's call it h or something. So you could specify the flux either by heating, supplying heat, or by removing heat and holding the temperature constant. It could be a combination of any of these. We'll start with the simplest case where we hold u equal to 0 on three sides and u equal to non-zero or f of x on the fourth side. Okay. If you are presented with a problem in which these are not zeros, I would actually ask you to I would ask you to do the same normalization to at least make one of them 0 to simplify it at least one bit. So your first step is always common to write the function is a product of two functions, f of x times g of y. Only difference is both x and y are spatial functions, so we won't treat them like time, we have to treat them like space. Okay, that's only. So x and y can be negative, positive, and so. So you would have d squared f over dx squared times g plus f times d squared g times dy squared equal to 0. We'll write it d squared f over dx squared 1 over f equal to minus 1 over g d squared g over dy squared, and that is equal to some k, which is a constant which we'll determine. The book writes this constant as minus k, so we'll also adopt that to keep it consistent. So we have second derivative with respect to x plus kf equal to 0, and second derivative with respect to y minus kg equal to 0. You want to now split the boundary conditions. Okay. So when you have u equal to 0, let's consider this side here with 0 less than x less than L and y equal to 0. U, which is f of x times g of y, is 0, would imply f of x is equal to 0. That is one of the boundary conditions. Wait. No, that would mean we want to write g at y equal to 0 is 0, which would be one of the boundary conditions. Like if you're splitting this for g, this is like writing g equal to 0. Okay. Again, u equal to 0 on this face with x equal to 0 and 0 less than y less than L. What would that mean? F of 0 times g of y equal to 0. If we assume in general g of y is non-zero, this implies f of 0 equal to 0. That is this side. By the same logic, on the other side, u equal to 0 with x equal to L and 0 less than y less than L implies f of x equal to L equal to 0. So I have used up 3 of the simple boundary conditions with the top remaining, which is u of x comma L equal to f of x. That is like writing f of x times g of L equal to f of x. We won't try to split this. We'll try to use it as the final step to figure out one of the Fourier coefficients. So anyway, these especially these two are now required for us to move forward with this solution. So I have f double prime plus kf equal to 0, f of 0 equal to f of L equal to 0. So this is f of x equal to, I just want to use the same notation, equal to, you can write this a cos kx plus b sin kx. Right? You don't feel lost because we saw this differential equation in the first lecture. Getting the characteristic equation, recognizing it as complex roots, and then writing the trigonometric solution. All that I'm writing in one step, assuming you would be okay with. So now you want to use the boundary conditions, which will imply f of 0, which is 0, equal to a plus b times 0, which can only mean a is 0. and f of L equal to 0 implies B sine KL equal to 0. We saw this already when we did the wave equation, that this B will be multiplied with one more constant. So I'm going to stop referring to this B for a while, because a constant will anyway be coming up when we do the other solution. Okay, so sine KL is 0, so KL should be n pi over L, or K should be n pi over L. So I have a solution f of x, which is sine n pi x over L. And since this function depends on n, I'm going to add a subscript n, because fn of x represents, or I shouldn't say represent, is a set of orthogonal functions that can be used to construct a general solution of f double prime plus kf equal to 0, as well as the original PDE for u. They also want to note n equals 1, 2, 3, and so on. Okay. So if we take the other equation, d squared g over dy squared minus kg, and k happens to be n pi over a squared. Oh, this should be square root of k. Because if this is your equation, this implies lambda squared plus k equal to 0, implies lambda is plus minus I square root of k. So this is square root of kx, square root of kx, square root of kl. So this is square root of k, which implies k is squared of this, n pi over L squared. So we have d squared g over dy squared minus kg equal to 0, or d squared g over dy squared minus n pi over a squared times g equal to 0, which would mean what? What will be the form of g of y? This is a positive number, so your characteristic equation is lambda squared minus n pi over L squared, which implies lambda is plus minus n pi over L, positive numbers. So g of y would be, let's call it c, exponent of n pi y over L plus t exponent of minus n pi y over L. Our domain is not infinite in the sense y has a bounded value of L. So whatever this exponent of n pi y over L is, the weighting constant C will adjust itself to keep the function smooth and finite. So we don't have to be scared of the positive exponent. All right, so this function obviously depends on n. So this is a potential basis function. In principle, you have to take this function over this interval 0 to L and establish the fact that this can be an orthogonal function. Okay, you have to try it. If we don't try that here, let's move forward to right. So you have Fn of x times Gn of y, which is sine n pi x over L multiplied by, I have C, and since this has an n, I'm going to add a subscript to the C and D as well. Cn exponent of n pi y over L plus Dn exponent of minus n pi y over L. This is my un of x comma y.
Wouldn't it be simpler to write G as a hyperbolic function?
Yeah, you can write. Okay. There is still two boundary conditions which we have not used so far. Okay. So we can write G of 0 equal to 0. G of 0 equal to 0. So wherever and G of 0 equal to 0 and x can be anything. So we would have, actually wait, hold on. Before we go from here, if we use the boundary condition G of 0 equal to 0, what do we get? Cn plus Dn equal to 0. Right? Or Dn is just negative exponent of or negative of Cn. It reduces the number of variables by 1. So, like he said, we can write Gn of y is Cn exponent of n pi y over L minus exponent minus n pi y over L, which would be 2Cn times hyperbolic sine of n pi y over L, or you could just leave it like this. It doesn't matter. Either way is okay. Yeah. Now we will write un of x comma y is f of x times fn of x times gn of y, which is sine n pi x over L times Cn times exponent of n pi y over L minus exponent of minus n pi y over L. And this is just un of x. If you write u of x comma y is the Fourier series summed over n from 1 to infinity. This will be n equals 1 to infinity Cn sine n pi x over L times exponent of n pi y over L minus exponent of Now we use the last boundary condition, the last remaining boundary condition. So if we write u of x comma 0 equal to, sorry, u of x comma l equal to f of x, this implies f of x equal to summation n equal to 1 to infinity. I have sine n pi x over L times Cn times, I have to substitute y equal to L, right? So that is like writing e power n pi minus e power minus n pi. You can call the whole thing something like alpha n. So this is summation n equal to 1 to infinity alpha n sine n pi x over L, which would mean alpha n equals 2 over L, 0 to L, f of x sine n pi x over L dx, or your Cn is 2 over L times e power n pi minus e power minus n pi times 0 to L of course, we took a square domain, the book does a rectangular domain. That's the difference. All right. This is the procedure. First step, what I would urge you to try is to look for how much can you simplify your boundary conditions. Try to have as many boundary conditions which are either 0 or 1, so that you would have a simpler time later. Okay. Then, of course, you still have to deal with whatever complexity the problem throws in.
So let's say like that u on the left side doesn't equal 0. Would you give an example of how you would normalize it to 0?
Sure. Can I erase this part? So if we have a set of boundary conditions, so we could have something like u equal to 0, u equal to 0, say for example, u equal to u1, and then u equal to f of x. One thing I would do right away is define a new variable, I'll call it u star or something, which is u divided by u1. If I can't get this to be 0, at least I can make it to be 1. So my scaled variables will be 0, 0, 1, and over here this is u star is f of x divided by u1. At least get a 1 in there. So the key difference would be when you get the first equation for f, your equation is going to look like this: d squared f over dx squared plus kf equal to 0, which will give you f of x equal to a cos square root of kx plus b sine square root of kx, with f of 0 equal to 0 and f of L equal to 1. Of course, we want to use the 0 first. That would mean a is still 0. That is a times 1 plus b times 0 equal to 0, which makes a is 0. It still gets you get rid of at least one part of the function. So then we have f of L equal to 1, which implies b sine square root of k times L equal to 1. And by the same logic, we don't have to track a b because you will anyway have another constant appear later. So this is like asking what values of square root of kl will lead you to pi by 2, 5 pi by 2, basically pi by 2 plus 2 pi power n, 2 pi power n minus 1, right? Because sine 3 pi by 2 will be negative 1 and 5 pi by 2 will again be positive 1 and so on. So this is essentially the sine curve. So you have your pi by 2 here, your 3 pi by 2, and then you have your 5 pi by 2. This is like drawing a line through here. Function takes these values only.
Should be 2 pi times and
2 pi times. 2 pi times n minus 1. It's a little bit simpler than what you would have otherwise, I guess. If you had, for example, u1 here, and maybe u equals u2, something like that here, you have to pick one. You won't get any more advantage by normalizing. You can only zero out one of them, or make only one of them to be 1, and this could still remain 0 and so on. So this would be something like you can define u star is u2 over u1, and u star on this side is 1, and this side is 1. This side is over u. Something like that. Not all of them can be solved by hand, because once you get an equation like a transcendental equation, say suppose this sine square root of kl equal to some alpha, some real number. To solve this, you can't just do it analytically because it's a nonlinear equation. You have to either use a graphical technique or Newton-Raphson or some kind of iterative technique. So not everything is like straightforward. In fact, one exercise that you can try at home is to take the Bessel functions Jn of x, try to get the zeros or the roots of the Bessel function. We'll soon need it when we do the cylindrical equation. So to practice problems related to this, again, I would refer you to problem set 12.6. Problem set 12.6, problems 18 to 25. So this was a unsteady or steady state equation. Recall that the equation we wrote is in terms of only the two spatial coordinates. So there is no time dependence here. This is usually used to model something that is at steady state. Okay. If you want to look at an unsteady problem or something that evolves over time, you would multiply this by c squared. This is the unsteady heat equation. Or you can also think about the wave equation in two dimensions. Obviously, the complexity goes up. The main complexity we are going to see is we are going to see what is called as a double Fourier series, because you have time and two spatial coordinates. Not only is our function going to depend on n, it's going to also depend on another integer, the way it works out. So we are not, instead of seeing both equations, we'll just discuss one. I think we'll discuss the wave equation. Whatever we do for wave equation applies for the heat equation as well, except what? The form of the solution for wave equation and heat equation differ in just one aspect. Because of the first derivative with respect to time, this will be a decaying exponent. Any unsteady problem would have a decaying exponent, whereas the wave equation will have trigonometric functions. That's the main difference. Okay. Otherwise, the procedure is the same.
That all unsteady problems will have a decaying exponent, while I didn't hear the second part of it.
The all heat equation or diffusion problems will have a decaying exponent because the derivative with respect to time is only to first order. All wave equation problems will have trigonometric solutions because the only way you can get a second derivative to be equal to this is to have trig functions so that the second order derivative continues to have some finite value. All right. So we'll start with this, and hopefully by today we'll be done with Cartesian coordinates. Okay, we'll see. Obviously, when we are dealing with domains which are easier to describe in a Cartesian coordinate system, like for example, if you have a square domain or a rectangular domain, it makes much more sense to use the Cartesian coordinate system, and we'll do the other domains soon. So we have this function given to us, and this is like a set of boundary conditions which assumes 0 on all sides. Okay. What would be the, like, okay, once we assume the solution to be 0 on all sides, which is our boundary condition, and as initial conditions, we assume u of x comma t is x comma t equal to 0 is g of x, and ut of x comma 0 is f of x and g of x. Initial velocity and displacement. One more mistake I made is u of x comma y comma t is f of x comma y, and ut of x comma y comma t equal to 0 is g of x comma y. We start by saying separating variables. We'll assume u of x comma y comma t is a product of two functions f of x comma y and g, which has all the time dependence built in. So we would have f times g double dot equal to c squared partial derivative with respect to x plus partial derivative with respect to y multiplied by g. So we'll rewrite this g double dot over c squared g equal to 1 over f or minus 1 over f partial f over partial y. Sorry, partial f plus partial y. Wait. This and we'll say this is equal to negative nu squared, where nu is a real number. So we would get g double dot plus c squared nu squared g equal to 0, which would give g of t equal to a cos c nu t plus b sin c nu t.
Before you remove that, have a question.
Yeah.
You say right there that FL is equal to 1 for your body conditions right here on the body.
Which one?
Yes.
One? Yes.
I guess that cannot be correct because our U is F times G and G is in the form of
No, this was for another problem.
yes, I see. I have that question.
Do you want me to go back and talk about that?
I think that may be incorrect.
Well, we are in the middle of that. Can we come back to this later?
Okay.
Why there is no negative sign?
Sorry? Oh, because this is the form of the equation. There is, we didn't, this derivative happens to be on the left side. We don't have to move them around. All we need to do is bring the g to the other side. So that's why there is no negative sign.
This equation is not putting by derivative the u.
No, we are substituting this into the original PDE, and then we are, for wherever u appears, you replace it with fg. So you get fg double dot, and then you have c squared times g times this. So we leave this hanging for a while to come back and write partial f over partial y plus nu squared f equal to 0. This is a PDE by itself and it has a name called the Helmholtz PDE. Helmholtz equation. And there we assume the function f, which depends on x and y, is a product of two functions, h and q. So we'll write t squared h over dx squared times q plus h times d squared q times dy squared plus nu squared hq equal to 0. Or we'll write it as 1 over h d squared h over dx squared equal to negative of 1 over q d squared q over dy squared plus nu squared, and this will say equal to minus k squared. So you get two ODEs, d squared h over dx squared plus k squared h equal to 0 and we have d squared q over dy squared plus q times k squared minus nu squared equal to 0. Is that correct? So I'll have minus this. Let's write it like this. Minus nu squared q plus k squared q equal to 0, which is d squared q dy squared plus q into q squared minus k squared equal to 0. Is that correct? Yeah. And this we'll call it t squared. So we have d squared q over dy squared plus p squared q equal to 0. So this equation for h and q rely only on the boundary conditions. They don't have any time dependence, so the initial conditions don't figure in here. What are your boundary conditions? It's 0 on all sides. That's what we started with. If you want to take a picture so you can. Yeah.
Is there any specific reason that we keep the new scale you normally change?
There is no specific reason. If you did the other way, physically you should get a solution which gives you the same value, although the functional form can slightly vary. There is no sanctity to one direction over the other. So if whatever treatment, if I swap the symbols, it should still hold. Okay. All right. So what are your boundary conditions? We assume that u is 0 on all sides. That's what we started with. That is the boundary condition. So if you use that, what can you simplify? This will be plus k squared h equal to 0, which implies h of x is a cos kx plus b sin kx. If you use h of 0 equal to 0, this will imply a is 0, and if h of l is 0, this would imply sin kl equal to 0 or k equals n pi over l. Now, by assuming a square, I've introduced a simplification without realizing. Okay, that is, you have k equals n pi over l. Now do this for the second equation, d squared q over dy squared plus p squared q equal to 0. Q of y is c, we'll write this as cos py plus d sin py. D sin py. By the same logic, you are going to get if q of 0 equal to 0, which should imply c is 0, and if q of I introduced L. Okay, in the book you get this length to be A and this length to be B. So if you want a solution process or an expression for a rectangular domain, the book has it. We'll just stick to a square domain which slightly simplifies it. So q of L equal to 0 implies d sin PL equal to 0, or you have PL equals m pi. Reason I introduce a second variable m or second integer m counter is this solution is completely independent of this solution. The fact that we got sin PL is 0 had nothing to do with sin KL is 0. So we have to use a different integer. So I have h of x equal to, I have sin n pi x over L, and since this depends on n, I'm going to introduce hn of x equal to that. Okay, and I also have q of y equal to sin m pi y over L, and since this depends on an integer m, I'll introduce a coefficient m. And if you recall, this had a constant b and this had a constant d, which we'll combine and write hn of x times qm of y is, we can call it b m comma n sin n pi x over L sin n pi y over L. Okay, sin m pi y over L. Yeah.
This square is positive, where you selected P2 with P square.
So you're asking how is this positive? Good question. Just think. So where did we get mu squared from? We got mu squared by splitting the original PD, right? And k squared was introduced when you split it for the second time here. So the way these type of solutions work is that you consider only the values that are negative. You don't really seek the values. You assume that it is negative and then derive a solution, because the other case would be resulting in an exponential solution, which could sometimes lead to problems. Okay, so we'll write here, assuming mu squared is greater than k squared. Sorry, I missed that. So we would have u of x comma y to be a double summation n equals 1 to infinity, m equals 1 to infinity, bmn sine n pi x over L sine m pi y over L. And we need a formula for bmn. We didn't really go over this when we did Fourier series, so I'm just airdropping a formula. Airdropping a formula. This would be 4 times L squared, 0 to L, 0 to L, f of x comma y sine m pi x, sine m pi x over L sine n pi m pi y and n pi x over L dx dy. Wait, maybe I'm skipping too many steps today. Let's not do this right now, because this also includes the time dependence, which we haven't touched upon. So this step is wrong, but up to here we are okay. Up to here we are okay, which captures the spatial dependence. Now we have to return to the time domain to get the entire function. So hn times qy is sine m pi y over L and sine n pi x over L. That until that we are good. Right. Okay. So now we have go back to the equation for g double dot plus c squared u squared times g equal to 0. That is where we left it there. So we have our p squared equal to nu squared minus k squared, or we can write nu squared equal to p squared plus k squared. And we do know that p is m squared plus k is n squared times pi squared, or nu equals square root of m squared plus n squared times pi. Wait, pi over L squared over L. From the beginning, I have been talking about a square domain, but if you want to look for a rectangular domain, the book has the derivation, which will involve, instead of L, you're going to have m squared over a squared and n squared over b squared. But we have been like simplifying it without thinking about it. Okay? So this is your nu. Okay. So now g of t is, we'll call it say alpha cos c nu t plus beta sine c nu t. And obviously alpha cos c, what is nu? C pi t over L times square root of m squared plus n squared. And we'll write it omega t, where omega equals pi t over L square root of m squared plus n squared plus beta sine omega t. That is g, to which we'll now add the subscript m comma n. This is alpha m comma n. This is beta m comma n. You want to remember this omega is also a function of m and n. All right. So now to construct u of m comma n, x comma y comma t, we would need to multiply g of m comma n of time times h of n times q of m times y. And since this function already has two arbitrary constants, I'm not going to consider this. So I'll write this together. Alpha m comma n cos omega t plus beta m comma n sin omega t times sin n by x over L times sin m by y over L. So now the entire solution, since it depends on two indices, would be double summation so at this point, we have alpha mn and beta mn that need to be worked out. Consider the initial condition u x comma y comma t equal to 0 equal to f of x comma y. This would mean f of x comma y is double summation infinity. So I have to substitute t equal to 0, which will make beta go away. So I would have alpha m comma n multiplied by the two sine functions, sine n pi x over L sine m pi y over L. Instead of airdropping the formula, maybe next lecture I can give you some more details how this alpha is actually coming out. So right now we'll just write it here. And the other initial condition is partial u over partial time at time 0 is g of x comma y, initial velocity. So we'll write g of x comma y is equal to summation If I substitute, if I take the derivative and then substitute, this term goes away, whereas this will stay. I'll have beta m comma n times omega, which also depends on m comma n, multiplied by the two functions, sine n pi x over L, sine m pi y. Now we are again back to the question, how to get alpha and beta. Let us stop here and pick it up next lecture. If we figure out the formulas for alpha and beta, you get your entire solution, which depends on x, y, and time. Thank you.